As you sit here watching this video, something absolutely mind-bending is happening all around you. Galaxies, enormous collections of hundreds of billions of stars, are racing away from us at speeds that would make your head spin. But here is the part that should genuinely shock you. The galaxy known as GNZ11, which our telescopes have actually photographed, which we have actual spectroscopic data on, is currently moving away from Earth at roughly 2.2 times the speed of light. Let me say that again so it really sinks in. A real, observed, confirmed galaxy is receding from us at more than twice the speed of light. This is not science fiction. This is not a theoretical model sitting on some physicist's chalkboard. This is a measured, calculated, verified fact based on data from the Hubble Space Telescope and the James Webb Space Telescope. And GNZ11 is not even the most extreme example. There are objects in the observable universe that are rushing away from us at more than 3 times the speed of light. 3 times. The fastest speed that anything in the universe is supposed to achieve, and these galaxies are tripling it. Now I know what you are thinking. I know the question that just fired off in your brain, because it is the same question that baffled physicists for decades. If Albert Einstein, the greatest mind of the 20th century, proved that absolutely nothing can travel faster than the speed of light, then how is this possible? How can a galaxy, a massive physical structure containing billions of stars and planets and gas clouds, move faster than light itself? Is Einstein wrong? Did we get something fundamentally broken in our understanding of the universe? Or is there something far stranger, far more beautiful and far more terrifying going on here? The answer, my friends, is the third option. Something far stranger is happening. And by the time we reach the end of this video, you will understand exactly what it is. You will understand it so deeply that you will never look at the night sky the same way again. Because what is happening out there in the depths of space is not just a curiosity or a fun fact to share at dinner parties. It is the key to understanding the ultimate fate of everything that exists. Every star, every planet, every atom in your body is affected by what I am about to explain to you. But before we dive in, let me throw one more number at you that should absolutely shatter your intuition. The universe is 13.8 billion years old. We know this with extraordinary precision from multiple independent lines of evidence. 13.8 billion years. So you would think, logically, that the farthest thing we could possibly see would be 13.8 billion light years away. Right? Light has had 8 billion years to travel, so the edge of the observable universe should be 13.8 billion light years in every direction. That makes perfect sense. Except it is completely wrong. The actual radius of the observable universe is not 13.8 billion light years. It is 46.5 billion light years. The observable universe is 93 billion light years across. In a universe that is only 13.8 billion years old, how? How can we see things 46 billion light years away if light has only had 13.8 billion years to travel? This is not a contradiction. This is not an error. This is the direct, measurable consequence of the phenomenon we are about to explore together. And it is one of the most profound truths that human beings have ever uncovered about the cosmos. If you are the kind of person who looks up at the stars and wonders what is really going on up there, then this video is made for you. Hit that like button right now, subscribe to this channel, and I promise you what you are about to learn over the next hour and a half will fundamentally change how you understand the universe. Turn down the lights, get comfortable, maybe grab a cup of tea or coffee, because we are going deep, and I mean really deep, into the very fabric of reality itself. Let us start at the very beginning. Not the beginning of the universe, but the beginning of our understanding. Let us start with light. You have heard the number before. The speed of light is 299,792,458 meters per second. That is approximately 300,000 kilometers every single second. In 1 second, a beam of light could circle the Earth more than 7 times. It could reach the moon in about 1.3 seconds. It crosses the distance between the Earth and the Sun in roughly 8 minutes. That speed is so fast that for most of human history, people thought light travelled instantaneously. It was not until the 1600s that scientists began to suspect that light had a finite speed, and it took centuries more to measure it accurately. Now here is where Einstein enters the picture, and here is where things get really interesting. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would rewrite the laws of physics. His name was Albert Einstein, and the paper laid out what we now call the special theory of relativity. The core idea was revolutionary, but simple in its elegance. The speed of light in a vacuum is the same for all observers, no matter how fast they are moving. It does not matter if you are standing still or racing through space at half the speed of light. When you measure the speed of a beam of light, you will always get the same answer. 299,792,458 meters per second. Always, and from this single postulate, Einstein derived something extraordinary. He showed mathematically that nothing with mass can ever reach the speed of light, let alone exceed it. As an object with mass accelerates, its relativistic mass increases. The faster it goes, the more energy it takes to accelerate it further. As it approaches the speed of light, the energy required approaches infinity. You would need literally infinite energy to push even a single atom to the speed of light. It cannot be done. This is not a technological limitation that we might overcome with better engines someday. This is a fundamental law of nature woven into the mathematical fabric of the universe itself. So here we have an ironclad law of physics, tested and confirmed by over a century of experiments to extraordinary precision. Nothing travels faster than light. Period. And yet, we have galaxies moving away from us at 2-3 times that speed. Both of these statements are true simultaneously. Both are verified by observation and measurement. How can that be? The answer lies in a distinction so subtle, so profound, that it took the greatest minds in physics decades to fully appreciate it. And that distinction is this: there is a fundamental difference between moving through space and space itself moving. Let me explain this with an analogy that I think will make it crystal clear. Imagine you are an ant standing on a giant rubber sheet. You can walk across this rubber sheet, and your maximum walking speed is, say, 1 centimetre per second. That is your personal speed limit. No matter how hard you try, your little ant legs cannot carry you faster than 1 centimetre per second across the surface of this sheet. Now imagine that someone starts stretching the rubber sheet. They grab the edges and pull, and the sheet starts expanding in all directions. What happens? Well, if there is another ant standing some distance away from you on the same sheet, the stretching of the rubber between you and that other ant means the distance between you is increasing. And here is the crucial part. The speed at which that distance increases has nothing to do with how fast either ant can walk. If the sheet is stretching fast enough, the other ant could be moving away from you at 10 centimetres per second, even though neither of you can walk faster than 1 centimetre per second. Neither ant is violating the speed limit. Both ants are perfectly stationary on their local patch of rubber. It is the rubber itself that is expanding between them, and there is no speed limit on how fast the rubber can stretch. This is exactly what is happening in our universe. The galaxies are the ants. Space is the rubber sheet. The speed of light is the ant's maximum walking speed. No galaxy is actually moving through its local patch of space faster than the speed of light. If you could somehow stand on a planet in GNZ 11 and measure the local physics, everything would look perfectly normal. Light would travel at the same old 299,792,458 meters per second. The laws of physics would work exactly as they do here. But the space between that galaxy and our galaxy is expanding, and the rate at which that space is expanding, accumulated over billions of light years of distance, results in the total distance between us increasing at more than twice the speed of light. This is what physicists call the recessional velocity, and it is fundamentally different from the velocity of an object moving through space. Recessional velocity is not constrained by the speed of light, because it is not really a velocity in the traditional sense. It is a rate of increase of distance due to the metric expansion of space itself. This distinction between peculiar velocity and recessional velocity is one of the most important concepts in all of cosmology. Peculiar velocity is the actual motion of a galaxy through its local space. Galaxies do move through space, pulled by gravity toward other galaxies and galaxy clusters. These peculiar velocities are typically a few hundred kilometers per second, sometimes up to 1,000 or so, well within the speed of light. Recessional velocity, on the other hand, is purely a consequence of expanding space. It increases linearly with distance. The farther away an object is, the more expanding space there is between us, and the faster the total distance grows. At a certain critical distance, the accumulated expansion adds up to more than 300,000 kilometers per second, and beyond that distance, galaxies recede faster than light. Not because they are breaking any law of physics, but because the law they appear to be breaking does not apply to this situation. Einstein's speed limit governs local motion through space. It says nothing about what space itself can do. Now, this understanding did not come easily. It took one of the most dramatic scientific discoveries of the 20th century to even realise that the universe was expanding at all. And that story begins not with Einstein, but with a handful of astronomers who dared to challenge the most fundamental assumption about the cosmos, for most of human history, and indeed for most of the history of modern science. People assumed the universe was static. It was not expanding, not contracting, just sitting there, eternal and unchanging. This was not just a casual assumption. It was deeply embedded in the scientific worldview. Even Einstein himself, when he completed his general theory of relativity in 1915, was so convinced that the universe was static that he added a special term to his equations, a fudge factor called the cosmological constant, specifically designed to keep the universe from expanding or contracting. His equations naturally predicted a dynamic universe, one that would either expand or collapse, but Einstein could not accept this. The universe had to be static. So he added this cosmological constant, labelled with the Greek letter lambda, to force his equations to describe a universe that just sits there unchanged forever. He would later call this the biggest blunder of his career, but that comes later in our story. The first real hints that the universe might not be static came from an American astronomer named Vesto Slipher, working at the Lowell Observatory in Flagstaff, Arizona, between 1912 and 1917. Slipher painstakingly measured the spectra of what were then called spiral nebulae, fuzzy spiral-shaped objects in the sky that we now know are entire galaxies far beyond our own Milky Way. When you take the light from one of these objects and spread it out into its component colours using a prism or a diffraction grating, you get a spectrum. And in that spectrum, you see specific patterns of dark lines at very particular wavelengths, corresponding to the absorption of light by specific chemical elements like hydrogen, calcium, and sodium. Now here is the key. If the object is moving toward you, those lines shift toward the blue end of the spectrum, toward shorter wavelengths. This is called blue shift. If the object is moving away from you, those lines shift toward the red end, toward longer wavelengths. This is called redshift. It is the same principle as the Doppler effect with sound. When an ambulance races toward you, its siren sounds higher pitched. When it races away, the siren drops to a lower pitch. Light does the same thing. Approach means blue shift. Recession means red shift. Slipher expected to find a random mix of blue shifts and red shifts among the spiral nebulae. Some should be coming toward us, some going away, more or less randomly. But that is not what he found. Of the roughly 25 spiral nebulae he measured, the overwhelming majority showed redshift. They were almost all moving away from us. This was strange and unexplained, but Slipher's work did not receive the attention it deserved at the time. Then came Edwin Hubble. Hubble was working at the Mount Wilson Observatory near Pasadena, California, using the most powerful telescope in the world at the time, the magnificent 100-inch Hooker telescope. In the mid-1920s, Hubble made a breakthrough that changed astronomy forever. He was able to identify individual stars, specifically a type of star called Cepheid variables, in some of these spiral nebulae. Cepheid variables are special because they pulsate, brightening and dimming in a regular cycle, and the period of their pulsation is directly related to their intrinsic luminosity. This relationship had been discovered by Henrietta Swan-Leavitt, a brilliant astronomer working at the Harvard College Observatory, and her work was absolutely foundational to what followed. Because if you know how bright a star truly is, and you can measure how bright it appears from Earth, you can calculate exactly how far away it is. The dimmer it appears compared to its true brightness, the farther away it must be. Using Leavitt's period luminosity relationship, Hubble calculated the distances to several spiral nebulae and got a staggering result. They were incredibly far away, far beyond the boundaries of our Milky Way galaxy. This alone was a revolutionary discovery. It proved that the Milky Way was not the entire universe, as many astronomers had believed. There were other galaxies out there, other island universes, separated from us by vast gulfs of empty space. The universe was suddenly much, much larger than anyone had imagined. But Hubble did not stop there. He combined his distance measurements with the redshift data that Slipher and others had been collecting, and he found something astonishing. There was a relationship between the two. The farther away a galaxy was, the faster it was moving away from us. This was not random. It was a clear, linear relationship. A galaxy twice as far away was receding roughly twice as fast. A galaxy 3 times farther was receding 3 times faster. Hubble published this result in 1929, and it became known as Hubble's law, though in recent years it has been more accurately renamed the Hubble-Lemaitre law, in recognition of the Belgian priest and physicist Georges Lemaitre, who independently derived the same relationship from Einstein's equations in 1927, 2 years before Hubble's observational confirmation. The mathematical expression of this law is beautifully simple. The recessional velocity of a galaxy equals the Hubble constant multiplied by its distance. V equals h0 times d. The Hubble constant, h0, is the rate of expansion of the universe, expressed in units of kilometers per second per megaparsec. A megaparsec is a unit of distance equal to 3.26 million light-years. So if the Hubble constant is, say, 70 kilometers per second per megaparsec, it means that for every 3.26 million light-years of distance between us and a galaxy, that galaxy is receding from us at an additional 70 kilometers per second due to expansion. A galaxy 1 megaparsec away recedes at 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. You can see where this is going. At some sufficiently large distance, the accumulated expansion rate exceeds 300,000 kilometers per second, the speed of light. That critical distance is called the Hubble radius, or the Hubble sphere. With the current estimated value of the Hubble constant, the Hubble radius is roughly 14 billion light-years, or about 4,300 megaparsecs. Beyond that distance, everything is receding from us faster than light. And here is the thing that really blows your mind. The Hubble sphere is much smaller than the observable universe. The observable universe extends to about 46.5 billion light-years in every direction, remember? So the vast majority of the observable universe, everything between 14 and 46, 5 billion light-years away, is already receding from us faster than light. This is not some exotic edge case. It is the normal state of affairs for most of the universe we can see. Now I need to tell you about one of the most heated debates in modern science, because it directly relates to everything we are discussing. I mentioned that the Hubble constant, h0, is approximately 70 kilometers per second per megaparsec, but that word approximately is hiding a scientific crisis. There are 2 primary ways to measure the Hubble constant, and they give different answers, and the disagreement is tearing the cosmology community apart. The first method uses the cosmic microwave background, the ancient radiation left over from the Big Bang, which I will explain in detail later. The European Space Agency's Planck satellite measured the CMB with extraordinary precision, and by fitting the data to our best cosmological model, derived a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of plus or minus 0.5. That is an incredibly precise measurement. The second method uses the traditional distance ladder approach, building up distances step by step using various types of standard candles, from nearby Cepheid variable stars to distant Type 1 supernovae. The SHOES project, led by Nobel laureate Adam Riess, has used this method to determine the Hubble constant as 73.04 kilometers per second per megaparsec, with an uncertainty of about plus or minus 1.04. Now 67.4 and 73.0 might not sound that different, but given the incredible precision of both measurements and their tiny error bars, this discrepancy is enormous in statistical terms. It is roughly a 5 sigma disagreement, meaning there is less than a 1 in a million chance that this difference is due to random measurement error. Both teams have checked and rechecked their work obsessively. The James Webb Space Telescope was specifically used to verify the Cepheid measurements from Hubble, and it confirmed them. The tension is real. It is not going away. This is what cosmologists call the Hubble Tension, and it is one of the biggest unsolved problems in physics right now. If the measurements are both correct, and the disagreement is real, then it means our standard model of cosmology is missing something. There might be new physics at play that we do not yet understand. Some theorists have proposed early dark energy, a burst of dark energy in the early universe that could reconcile the two measurements. Others have suggested new types of particles or interactions that we have not yet detected. Some have even proposed modifications to Einstein's gravity. The honest truth is that no one knows the answer yet. This is an active, ongoing crisis in physics, and its resolution could lead to a revolutionary new understanding of the universe. When I tell you that this topic, the expansion of the universe and the recession of galaxies, is at the cutting edge of modern science, I mean it literally. Scientists are working on this right now, today, as you watch this video. Let me pause here and ask you something. Before this video, did you know that there was a crisis in measuring the expansion rate of the universe? Did you know that two of the most precise measurements in the history of science disagree with each other, and that this disagreement might be pointing toward entirely new physics? If this is blowing your mind, you are going to love what comes next. Drop a comment below telling me what you knew about the Hubble tension before watching this. And if you have not liked this video yet, now is a great time. We are about to go even deeper. Let us talk about the actual speeds involved, because I think putting real numbers on this makes it visceral in a way that abstract concepts cannot. Let us start with GNZ11, the galaxy I mentioned at the beginning. GNZ11 has a measured redshift of approximately 11.09. What does that mean? It means that the wavelength of the light we receive from this galaxy has been stretched by a factor of about 12 to 9 compared to when it was originally emitted. The light has literally been stretched to more than 12 times its original wavelength during its journey through expanding space. From this redshift, using our cosmological models, we can calculate that GNZ11 is currently about 32 billion light-years away from us, not 13.4 billion, which is the look-back time, the amount of time the light has been travelling. The galaxy was much closer when it emitted the light we are seeing now, roughly 2.7 billion light-years away. But during the 13.4 billion years that light has been travelling toward us, the space between us and the galaxy has been expanding the whole time. So the galaxy has been carried much farther away. Its current distance is about 32 billion light-years, and it is receding from us at approximately 2.2 times the speed of light. But we can go further. The James Webb Space Telescope has discovered galaxies even more distant than GNZ11. The galaxy Jade's GS Z14-0, confirmed by Jubbist's spectroscopic instruments, has a redshift of approximately 14.32, making it one of the most distant objects ever observed. The light we see from this galaxy was emitted when the universe was only about 280 million years old, less than 2% of its current age. This galaxy is now even farther away than GNZ11 and receding even faster. And if we go to the absolute extreme, the cosmic microwave background radiation, the oldest light in the entire universe, was emitted from a surface that is now approximately 46 billion light-years away and is receding from us at more than 3 times the speed of light. More than 3 times. The fastest speed in the universe tripled. And that is how fast the most distant observable matter is moving away from us. And remember, this is not some exotic violation of physics. This is completely consistent with Einstein's general theory of relativity. In fact, it is predicted by it. Now here is a question that might have been nagging at you, and it is a brilliant question. If these galaxies are moving away from us faster than the speed of light, how are we seeing them at all? If their light can never reach us because they are receding faster than light can travel, how did we take pictures of them? How do we have spectroscopic data? This seems like a paradox, and resolving it requires understanding something quite subtle about how expansion works over time. When the light from GNZ11 was first emitted, 13.4 billion years ago, the galaxy was not 32 billion light-years away. It was only about 2.7 billion light-years away. And the Hubble sphere, the distance at which recession equals the speed of light, was smaller back then too. In fact, when GNZ11 emitted the light we are now seeing, it was already beyond the Hubble sphere of that time. It was already receding faster than light when it emitted that light. So how did the light reach us? Here is the beautiful subtlety. The photon, the particle of light, was emitted in our direction. But because the space between us and the galaxy was expanding faster than the photon could travel, the photon was initially being carried away from us. It was like a swimmer swimming upstream against a current that is faster than they can swim. The photon was moving toward us at the speed of light, but the space it was in was being carried away even faster. So at first the photon was actually getting farther from us, not closer. But the expansion rate of the universe is not uniform over time. The Hubble parameter, which measures the expansion rate, changes as the universe evolves. And crucially, the Hubble sphere grows over time in certain cosmological eras. As the Hubble sphere expanded outward, it eventually caught up with our struggling photon. At that point, the photon crossed from outside the Hubble sphere to inside it. Now it was in a region where the local expansion rate was less than the speed of light, and it could finally make progress toward us. From that moment on, the photon steadily approached, eventually crossing the billions of light-years of space to hit the mirrors of our telescopes. The journey took 13.4 billion years, but the photon made it. It is as if the swimmer, unable to fight the current, waited patiently as the river slowed down, and then finally was able to swim to shore. This means something remarkable. The boundary between what we can and cannot see is not the Hubble sphere, it is the particle horizon, a much larger boundary that accounts for the entire history of expansion. And the particle horizon of our observable universe, the maximum distance from which information could have reached us over the entire history of the cosmos, is those 46.5 billion light-years I mentioned earlier. The Hubble sphere is only about 14 billion light-years, so there is a huge shell of the observable universe between 14 and 46. 5 billion light-years that is currently receding faster than light, but whose ancient light has already reached us. We can see these objects, but only as they were in the distant past. We can never see them as they are now, and we can never send a signal that will reach them in their current state. Let us go deeper still. Let us talk about what space actually is, because this question is far more profound than it might seem at first glance. When I say space is expanding, what does that mean physically? What is it that is expanding? Is space a thing, a substance, a fabric, or is it just the absence of things, an empty stage on which matter performs its dance? In Newtonian physics, space was absolute and unchanging. It was a rigid, infinite stage, and objects moved around on it. Time ticked uniformly everywhere. Space was just the void, the emptiness between things. But Einstein's general theory of relativity, published in 1915, completely reimagined space. In general relativity, space and time are not separate, absolute entities. They are woven together into a single four-dimensional structure called spacetime, and spacetime is not a passive stage. It is a dynamic entity that curves, warps, ripples, and expands in response to the matter and energy it contains. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. This is gravity. Not a force pulling objects together through empty space, but a consequence of objects following the straightest possible paths through curved spacetime. The Earth does not orbit the Sun because the Sun pulls on it with some invisible force. The Earth orbits the Sun because the Sun's mass has curved the space-time around it, and the Earth is simply following the natural geometry of that curved space-time, and if space-time can curve and warp, it can also expand. The equations of general relativity describe the large-scale behaviour of space-time, and when applied to a universe filled with matter and energy distributed roughly uniformly, they produce solutions that describe an expanding or contracting space-time. This is not some marginal speculative prediction. It is the most natural, straightforward solution to Einstein's field equations. A static universe requires special conditions, a precise balance. An expanding or contracting universe is the default. The mathematical framework that describes this expanding universe is called the Friedmann-Lemaitre-Robertson-Walker metric, or flow metric for short, named after 4 scientists who contributed to its development. Alexander Friedmann, a Russian physicist, derived the key equations in 1922. Georges Lemaitre, the Belgian priest and physicist I mentioned earlier, independently derived similar equations in 1927 and connected them to astronomical observations. Howard Robertson and Arthur Jeffrey Walker later proved that this was the most general metric consistent with the cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales. At the heart of the flow metric is a quantity called the scale factor, usually denoted by the letter A, and written as a function of time, A of t. The scale factor is a single number that tells you how much the universe has expanded at any given time compared to some reference time. By convention, we set it equal to 1 at the present time. At earlier times, A was smaller. At the moment of the Big Bang, A was effectively 0, meaning all distances were compressed to 0. As the universe has expanded, it has grown, and all distances between gravitationally unbound objects have been scaled up by this factor. If the scale factor doubles, every distance in the universe doubles. If it triples, every distance triples. This is the metric expansion of space. Not an explosion outward from some centre, but a uniform scaling up of all distances everywhere. The rate at which the scale factor changes is what determines the expansion rate of the universe. The Hubble parameter, which I have been calling the Hubble Constant, is technically not constant at all. It changes over time. It is defined as the time derivative of the scale factor divided by the scale factor itself. At any given moment, it tells you the expansion rate. But that rate has been changing throughout cosmic history. The value we call h0 is just the current value of this parameter. Now, a critical question is, what determines how the scale factor changes over time? What governs the expansion history of the universe? The answer comes from the Friedmann equations, which relate the expansion rate to the energy content of the universe. And the universe contains different types of energy, each of which affects expansion differently. The first type is radiation. This includes photons, neutrinos, and any other massless or nearly massless particles travelling at or near the speed of light. In the early universe, when it was extremely hot and dense, radiation was the dominant form of energy. In a radiation-dominated universe, the expansion decelerates relatively quickly. The scale factor grows proportionally to the square root of time. The second type is matter. This includes all the atoms, all the dark matter, all the stuff with mass that fills the universe. As the universe expanded and cooled, the energy density of radiation dropped faster than the energy density of matter, and matter became dominant. In a matter-dominated universe, expansion still decelerates, but more slowly than in the radiation era. The scale factor grows proportionally to time raised to the 2/3 power. And then there is the third type, the one that changes everything. Dark energy. This mysterious form of energy does not dilute as the universe expands. While the density of matter drops as space expands and matter gets spread out over a larger volume, and radiation drops even faster, the density of dark energy remains roughly constant. This means that as the universe gets bigger, dark energy becomes an increasingly dominant fraction of the total energy, and unlike matter and radiation, dark energy does not cause expansion to decelerate. It causes expansion to accelerate. In a dark energy-dominated universe, the scale factor grows exponentially, faster and faster and faster, without limit. And here is the kicker. We live in a dark energy-dominated universe. Right now. The transition happened roughly 5 to 6 billion years ago. Before that, matter was dominant, and the expansion of the universe was gradually slowing down, decelerating as the gravity of all the matter in the universe pulled against it. But about 5 billion years ago, dark energy took over, and the expansion began to accelerate. The universe is not just expanding, it is expanding faster and faster with every passing moment. The discovery that the universe's expansion is accelerating was one of the most shocking and revolutionary findings in the history of science. It happened in 1998, and it came from a completely unexpected direction. 2 independent teams of astronomers were studying distant Type 1a supernovae. These are a particular type of stellar explosion that occurs in binary star systems and has a remarkably consistent intrinsic brightness, making them excellent standard candles for measuring cosmic distances. The Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Ries, were both trying to measure how much the expansion of the universe was decelerating. Everyone expected to find deceleration. The gravitational pull of all the matter in the universe should be gradually slowing the expansion, like a ball thrown upward gradually slowing under Earth's gravity. The only question was how much deceleration. But when both teams analysed their data, they found something nobody expected. The distant supernovae were dimmer than predicted. Dimmer than they should have been if the universe were decelerating. Dimmer than they should have been even if the universe were expanding at a constant rate. The only explanation was that the expansion was accelerating. The supernovae were farther away than expected, because the expansion had been speeding up. Both teams checked their data exhaustively, terrified of announcing such an extraordinary result and being wrong. They independently reached the same conclusion. The expansion of the universe is accelerating. This result was so unexpected, so contrary to all theoretical expectations, that it sent shockwaves through the physics community. The only way to explain accelerating expansion within the framework of general relativity was to invoke some form of energy with negative pressure, an energy that pushes space apart rather than pulling it together. This energy was given the name dark energy, and it is without question one of the greatest mysteries in all of science. Let me tell you what we know, and more importantly, what we do not know about dark energy. We know it exists. The evidence is overwhelming, coming not just from supernova observations, but from the cosmic microwave background, from the large-scale structure of the universe, from baryon acoustic oscillations, and from gravitational lensing. Multiple independent lines of evidence all converge on the same conclusion. Roughly 68% of the total energy content of the universe is in the form of dark energy. Dark matter makes up about 27%. And ordinary matter, the atoms that make up you, me, the Earth, the stars, everything we can see and touch, makes up a mere 5%. We are an insignificant minority ingredient in a universe dominated by things we do not understand. We know that dark energy has a property called negative pressure. In general relativity, both energy density and pressure contribute to gravity. Normal matter has positive energy and positive or zero pressure, and both of these contribute to gravitational attraction. But dark energy has positive energy density and large negative pressure, and the effect of the negative pressure overwhelms the effect of the positive energy, resulting in a net repulsive gravitational effect. It pushes the universe apart, and the more space there is, the more dark energy there is, because its density remains constant as space expands, and the stronger the repulsion becomes. It is a runaway process. The simplest explanation for dark energy is Einstein's cosmological constant, the very same lambda that Einstein introduced to keep the universe static, and then discarded as his biggest blunder. In a delicious irony, it turns out that some form of the cosmological constant may actually exist, though not for the reason Einstein intended. If dark energy is the cosmological constant, it represents a constant intrinsic energy density of the vacuum of space itself. Every cubic metre of space, no matter where it is or what it contains, has the same tiny amount of energy. This energy density is astoundingly small, about 6 times 10 to the negative 10 joules per cubic metre. That is an incomprehensibly tiny amount of energy in any given volume of space, but the universe is very, very big, and there is an unimaginable amount of space. Added up across the entire universe, this tiny energy density dominates everything else. But here is something that haunts physicists to this day. Quantum field theory, our best theory of the subatomic world, predicts that the vacuum should have energy. Virtual particles constantly pop in and out of existence, and their combined effect should produce a vacuum energy. Great, that sounds like it could explain dark energy. Except when you calculate the vacuum energy predicted by quantum field theory, you get a number that is roughly 10 to the 120 times larger than the observed value of dark energy. That is a factor of 1, followed by 120 zeros. This is sometimes called the worst prediction in the history of physics. It is not just a little off, it is off by 120 orders of magnitude. Something is catastrophically wrong with our understanding of how to connect quantum mechanics to gravity and cosmology. This is called the cosmological constant problem, and it remains unsolved. Now, the cosmological constant is the simplest model for dark energy, and it fits the current data reasonably well, but it is not the only possibility. Some physicists have proposed that dark energy might not be constant at all. It might be a dynamic field that changes over time, sometimes called quintessence. In these models, there is a new quantum field, similar to the Higgs field, but different, that permeates all of space and whose energy drives the acceleration of expansion. The key difference is that quintessence can change, evolve, and potentially even switch from repulsive to attractive behaviour over cosmic time. To distinguish between a cosmological constant and dynamic dark energy, scientists use a parameter called the equation of state parameter, represented by the letter W. This parameter describes the relationship between the pressure and energy density of dark energy. For a cosmological constant, was exactly -1. For quintessence models, was greater than -1, meaning the dark energy is somewhat less repulsive and weakens over time. And for a terrifying class of models called phantom energy, W is less than -1. Meaning the dark energy grows stronger and more repulsive over time. The current observational data suggests that W is very close to -1, consistent with a cosmological constant, but there have been tantalizing hints that it might not be exactly -1. The Dark Energy Spectroscopic Instrument, known as DESI, has been surveying millions of galaxies to measure the expansion history of the universe with unprecedented precision. Its early results have shown hints, preliminary but intriguing, that dark energy may indeed be changing over time. If these hints hold up with more data, it would be a seismic shift in our understanding of cosmology. It would mean dark energy is not a simple constant, but a dynamic entity with its own physics that we need to understand. The implications would be enormous. Why does the value of W matter so much? Because it determines the ultimate fate of the entire universe. That single number, the equation of state of dark energy, is quite literally the most consequential number in all of existence. I will come back to this later when we discuss the possible futures of the cosmos, and trust me, some of them are genuinely terrifying. If this video is making your brain tingle, if you are feeling that sense of wonder and awe that comes from glimpsing the true scale and nature of reality, do me a favour and hit that like button. Subscribe if you have not already, and drop a comment telling me what is blowing your mind the most so far. Is it the superluminal recession? The Hubble tension? The vacuum energy catastrophe? I want to know. Let us keep going. I want to make sure we have a crystal clear understanding of the observable universe and its boundaries, because there are several different boundaries in cosmology and they are often confused with each other, even by people who should know better. The first and most important boundary is the particle horizon. This is the maximum distance from which light or any other signal could have reached us since the beginning of the universe. It defines the edge of the observable universe. The particle horizon is currently about 46.5 billion light-years away, corresponding to the cosmic microwave background. Nothing beyond this distance has had time to send us any signal, no light, no gravitational waves. Nothing. We are completely ignorant of what lies beyond. The second boundary is the Hubble sphere, which I have already discussed. This is the distance at which the recessional velocity due to expansion equals the speed of light. It is currently about 14 billion light-years away. Galaxies beyond the Hubble sphere are receding faster than light. But as I explained, the Hubble sphere is not the edge of the observable universe. We can and do see objects well beyond the Hubble sphere, thanks to the way expansion and light travel interact over cosmic time. The third boundary is arguably the most important and the most frightening. It is the cosmological event horizon. This is the boundary beyond which events happening right now can never, ever affect us in the future. It is different from the particle horizon, which tells us about the past. The event horizon tells us about the future. And in a universe with accelerating expansion, the event horizon is not the same as the particle horizon. The cosmological event horizon defines the maximum distance from which light emitted right now will ever be able to reach us. Beyond that distance, the accelerating expansion of space will carry the light away faster than it can approach, and it will never arrive. No matter how long we wait, not in 1 billion years, not in 1 trillion years, not ever. The cosmological event horizon is currently estimated to be about 16 to 17 billion light-years away in proper distance. And here is the chilling part: it is getting closer. Well, more precisely, in moving coordinates, the event horizon is shrinking. Fewer and fewer galaxies fall within the volume from which light can ever reach us. Every second, photons that are emitted from galaxies just beyond the event horizon are doomed. They will travel through space for eternity, always moving toward us, but the accelerating expansion will stretch the space between us faster than the photons can cross it. They will never arrive. They are lost to us forever. This means that the observable universe, as vast and magnificent as it is, represents a shrinking window of access. We are slowly, inexorably being cut off from more and more of the cosmos. Galaxies that we can see today, whose light is reaching our telescopes right now, will eventually fade from view. Their light will be redshifted to longer and longer wavelengths, stretched by the relentless expansion of space, until it becomes radio waves, then infrared, then wavelengths so long that no conceivable telescope could detect them. The galaxies will dim, redden, and eventually vanish from our observable universe entirely. And there is nothing we can do about it. No technology, no spacecraft, no future advance in physics can overcome the accelerating expansion of space itself. You cannot outrun the expansion because you would need to travel faster than light, and nothing physical can do that. The galaxies are not moving away through space at superluminal speeds. The space itself is expanding, and there is no way to counteract that on cosmic scales. This brings us to one of the most poignant and philosophically profound consequences of accelerating expansion. It is a thought experiment first articulated clearly by cosmologists Lawrence Krauss and Robert Scherer. Imagine a civilization arising in the far future, say 100 billion or 1 trillion years from now. By that time, the accelerating expansion will have carried all galaxies beyond our local group, the small cluster of galaxies that includes the Milky Way and Andromeda, far beyond the observable universe. The Milky Way and Andromeda will have merged into a single large elliptical galaxy, sometimes called Milkomeda, and that galaxy will be alone, completely alone in an observationally empty universe. The future astronomers of this civilization will look out into the sky and see their own galaxy, the merged Milkomeda, surrounded by perfect absolute darkness. No other galaxies, no cosmic microwave background, because it will have been redshifted to wavelengths so long as to be utterly undetectable. No evidence of the Big Bang, no evidence of expansion, no evidence of any of the cosmological revelations that we have been discussing in this video. These future astronomers will construct a cosmology based on what they can observe, and their cosmology will be completely wrong. They will conclude that the universe consists of a single galaxy surrounded by infinite, eternal, empty space. They will have no way to know that billions of galaxies once filled the sky. They will have no way to discover dark energy, or the Big Bang, or the expanding universe. The evidence will be gone, swept away by the very expansion it testified to. And here is the deeply unsettling question that follows. Are we in a similar situation? Is there evidence of some fundamental aspect of the universe that has already been erased by cosmic evolution, that existed in some earlier epoch but has faded beyond our ability to detect? Are there truths about reality that were observable 1 billion years ago but are no longer accessible to us? We have no way to know. We can only observe what is observable from our particular vantage point in space and time. And our vantage point, while extraordinary by future standards, may already be missing pieces of the puzzle that we cannot even conceive of. Let me now take you back in time, all the way back, to talk about the oldest light in the universe and what it tells us about cosmic expansion. The cosmic microwave background radiation, or CMB, is one of the most important discoveries in the history of science, and it provides some of the most powerful evidence for everything we have been discussing. About 380,000 years after the Big Bang, the universe underwent a dramatic transition. Before this moment, the universe was so hot that atoms could not exist. Electrons and protons were flying around separately in a searingly hot plasma, and photons, particles of light, were constantly bouncing off the free electrons, unable to travel in a straight line for any appreciable distance. The universe was opaque, like being inside a thick glowing fog, but as the universe expanded, it cooled, and at about 380,000 years, the temperature dropped below roughly 3,000 Kelvin, cool enough for electrons to combine with protons to form neutral hydrogen atoms. This process is called recombination, despite the fact that it was the first time electrons and protons combined, not a recombination. Once the electrons were bound inside atoms, the photons were free. They could travel unimpeded through space. The universe became transparent. Those photons, released in that moment of recombination, have been travelling through space ever since. For 13.8 billion years, they have been streaming through the expanding universe, and we can detect them today. They fill every corner of space, coming from every direction. They are the oldest light in existence, the afterglow of the Big Bang itself, but they have been changed by their journey. When they were released, they had a temperature of about 3,000 Kelvin and were predominantly visible light, glowing with a warm orange-red colour. But during their 8 billion year journey, the space they travelled through expanded enormously. Their wavelengths were stretched, redshifted by the expansion. What started as visible light has been stretched all the way to microwave wavelengths. The temperature of these photons is now just 2.725 Kelvin, barely above absolute zero. The existence of this radiation was predicted in the late 1940s by George Gamow, Ralph Alpha, and Robert Herman, based on theoretical calculations of what conditions would have been like in the early universe. But the prediction was largely forgotten until 1964, when Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in New Jersey, accidentally detected it. They were testing a new microwave antenna and found a persistent background noise that they could not explain. It came from every direction in the sky, at every time of day and night, and it would not go away. They checked everything. They thought it might be interference from New York City. They thought it might be pigeon droppings on the antenna. They cleaned the antenna. They checked for every possible source of error. The noise persisted. They eventually learned that a group of physicists at nearby Princeton University, led by Robert Dick and Jim Peebles, had been specifically building a detector to look for exactly this radiation. Penzias and Wilson had scooped them by accident. The discovery earned Penzias and Wilson the Nobel Prize in Physics in 1978, and it provided some of the strongest evidence that the Big Bang theory was correct. Since then, the CMB has been studied with increasingly sophisticated instruments. The COBE satellite, launched in 1989, showed that the CMB has an almost perfectly uniform temperature across the sky, with tiny fluctuations of only about 1 part in 100,000. The 2MAP satellite, launched in 2001, mapped these fluctuations in much greater detail, and the Planck satellite, launched in 2009, produced the most precise and detailed map of the CMB ever made. These tiny temperature fluctuations, barely detectable variations of a few millionths of a degree, are the seeds of all the structure in the universe. The slightly denser regions in the early universe, corresponding to slightly warmer spots in the CMB, gravitationally attracted more matter over billions of years, growing into the galaxies, galaxy clusters, and vast cosmic structures we see today. The slightly less dense regions became the great cosmic voids, enormous bubbles of nearly empty space, hundreds of millions of light-years across. The CMB is directly relevant to our discussion of superluminal recession because it provides the most extreme example. The surface of last scattering, the region of space from which the CMB photons were released, has a redshift of approximately 1100. That means the light has been stretched by a factor of about 1101 since it was emitted. Using our cosmological models, we can calculate that this surface is now about 46 billion light-years away, even though the light has been travelling for only 13.8 billion years. And the current recessional velocity of this surface is more than 3 times the speed of light. The CMB is the most direct, most thoroughly measured, most precisely confirmed evidence that recessional velocities can and do exceed the speed of light. It is not speculative. It is observed. It is measured. It is real. Now let me take you even further back in time, to the very first instance of cosmic history, because there is another episode of superluminal expansion that makes even the current recession of distant galaxies look tame. I am talking about cosmic inflation. In the 1970s, cosmologists realised that the standard Big Bang theory, while enormously successful, had some troubling problems. 3 problems in particular demanded explanation. The first was the horizon problem. The CMB, as I mentioned, has an almost perfectly uniform temperature across the entire sky. Every direction you look, the temperature is the same to 1 part in 100,000. But here is the problem. In the standard Big Bang model, without inflation, regions of the CMB sky that are more than about 2 degrees apart were never in causal contact. They were too far apart for light or any other signal to have travelled between them in the time since the Big Bang. They could never have exchanged energy or information. So how did they reach the same temperature? It would be like walking into a room and finding 2 cups of coffee at exactly the same temperature to 5 decimal places, even though the cups had never been in contact and were on opposite sides of the room. You would immediately suspect that they had been in thermal contact at some earlier time. The second problem was the flatness problem. The geometry of the universe can be characterized by a parameter called omega, the ratio of the actual density of the universe to the critical density. If omega is exactly 1, the universe is geometrically flat, like a flat sheet. If omega is greater than 1, the universe is positively curved, like the surface of a sphere. If omega is less than 1, the universe is negatively curved, like a saddle. Observations show that omega is extremely close to 1. The universe is very, very flat. But in the standard Big Bang model, the value of omega tends to diverge away from 1 over time. If it starts even slightly above 1, it grows larger. If it starts slightly below 1, it shrinks towards 0. For omega to still be so close to 1 after 13, 8 billion years of expansion, it must have been extraordinarily close to 1 at the beginning, tuned to a precision of something like 1 part in 10 to the 60th power. That level of fine-tuning demands an explanation. The third problem was the monopole problem. Certain grand unified theories of particle physics predict that exotic particles called magnetic monopolies, particles with only a north or only a south magnetic pole, should have been produced in enormous quantities in the extreme conditions of the early universe. But we have never detected a single magnetic monopoly. Where did they all go? In 1981, a young physicist named Alan Guth proposed a revolutionary solution to all 3 problems at once. He proposed that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid, exponential expansion. This period, which lasted from roughly 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang, is called cosmic inflation. During inflation, the universe expanded by at least a factor of 10 to the 26th power. A region of space smaller than a proton was stretched to a size larger than the entire observable universe. The expansion during inflation was vastly, incomprehensibly faster than the speed of light. Not 2 or 3 times faster, not 1,000,000 times faster, The expansion rate during inflation was so extreme that numbers lose their meaning. Inflation solves all three problems elegantly. It solves the horizon problem because before inflation, the tiny region that inflated into our observable universe was small enough for all parts to have been in causal contact. They reached thermal equilibrium before inflation, and then inflation stretched that uniform region to enormous size, preserving the uniformity. It solves the flatness problem because inflation stretches space so dramatically that any initial curvature is diluted to insignificance, just as the surface of a balloon appears flat if you inflate it to an enormous size. And it solves the monopole problem because any monopoles produced before inflation were diluted to an immeasurably tiny density by the enormous expansion. The driving force behind inflation is thought to be a quantum field called the inflaton field. In its high-energy state, this field has a very high energy density that acts like a cosmological constant on steroids, driving exponential expansion. When the inflaton field decayed to its ground state, inflation ended, and the energy stored in the field was converted into a flood of particles and radiation, reheating the universe and producing the hot, dense state from which the standard Big Bang evolution proceeded. Inflation is a widely accepted theory, but it is important to note that it has not been definitively confirmed in the way that, say, the expanding universe or dark energy have been. The strongest evidence for inflation comes from the pattern of fluctuations in the CMB, which matches the predictions of inflationary models remarkably well. Inflation predicts a nearly scale-invariant spectrum of primordial fluctuations, which is exactly what Planck and other experiments have measured. Inflation also predicts that the universe should be geometrically flat, which is confirmed by observation. However, one of the key predictions of inflation has not yet been verified: the existence of primordial gravitational waves. Inflation should have produced gravitational waves, tiny ripples in space-time, that would leave a distinctive imprint on the polarization of the CMB. A pattern called B-mode polarization. Experiments like BICEP and the Keck array at the South Pole have been searching for this signal for years. In 2014, the BICEP-2 team announced a detection of B-mode polarization, sparking enormous excitement, but it was later determined that the signal was likely due to dust in our own galaxy, not primordial gravitational waves. The search continues, and a confirmed detection would be a smoking gun for inflation, possibly winning another Nobel Prize. So inflation represents the original superluminal expansion of space. It is a period when space expanded at rates so far beyond the speed of light that it boggles the mind, and it is the same fundamental phenomenon that we observe today in the recession of distant galaxies, just turned up to an unimaginable extreme. The physics is the same. Space expands. The speed of light limits objects moving through space, but not the expansion of space itself. Whether it is the gentle, steady expansion we observe now, or the violent, exponential expansion of inflation, the principle is the same. Now I want to bring us to the modern era and talk about how the James Webb Space Telescope is transforming our understanding of the distant, fast receding universe. The James Webb Space Telescope, or GEA, was launched on December 25th, 2021, and became fully operational in July 2022. It is the most powerful space telescope ever built, with a 5-meter primary mirror made of gold-coated beryllium segments and a suite of instruments designed to observe in the infrared part of the spectrum.